for designing FPT algorithms. It's called iterative compression. It's somewhat unique to FPT algorithms. What we have seen is branching, which is an age-old technique for designing exact algorithms. Sometimes it's called backtracking, branch unbound. So we've seen that. Iterative compression is a very beautiful technique which has helped us give a very efficient FPT algorithms for a number of problems which are open for quite some time. Okay. So what is the idea? Typically it is for minimization problems. I'll start with illustrating it in on vertex cover problem. So your input is graph G, the parameter is K, and the question is, does there exist a vertex cover of size at most K? So this is a standard vertex cover question where K is the parameter. Now I am also going to assume that for the input I am also given some solution S which is a vertex cover. I am given a solution, but it is of larger than K size, okay, some f of K size. So now it appears like a simpler problem because I am also given some vertex cover. So you have a lot more structure in the graph. You can exploit the fact that I am given a vertex cover. Now I am asking, is there a vertex cover of size at most K? Now in general, one question is who gives you this vertex cover, right? This is we will get to that later. There are many ways to get it. One is, for example, an approximation algorithm. The other is this one can get this through a notion of iterative way, which I will get to that later. For now, let us say I am given this using some approximation algorithm. So there are a number of ratio 2 approximation algorithms for vertex cover. So if my question is there a vertex cover of size at most K, I take the graph and feed it into one of those 2 approximation algorithm, and if such an algorithm gives me a vertex cover of size more than 2K, then I know that there is no vertex cover of size at most K, and so I can say no. Otherwise I have a vertex cover of size at most 2K. So at least for a vertex cover you can assume that this is at most 2K. How do I get this? Using a 2 approximation algorithm. Okay, for different problems you may get different approximations, so the f of k may be different. And as I said, approximation is not the only way to get such a solution. There are other ways. So you get some. I'm giving you some solution, and so the notion of compression. I give you a larger size solution. Can you compress it to get a smaller size solution? So that's the question. Okay. So for vertex cover, it turns out to be completely trivial. Okay, and we'll see it. It gets more involved for other problems. In particular, we will get to undirected feedback vertex set and design a C power k algorithm using this technique. So let's understand what is the structure now. I have a graph, but I am given a vertex cover whose size is at most 2K, and this is the remaining graph, right? What do I know about this induced subgraph? It's an independent set because this is a vertex cover. So this is the exploitation of the structure given to me, right? So this is my goal is to find a vertex cover of size at most K. There are no edges here, which is good news. So the edges are here are like this, and I need to pick k vertices to cover all these edges, and that is a question. Okay. So, what can I do? I mean, even without giving this, I know we have 2 power k or 1.6, 1.58 power k kind of algorithm, but so we will actually get an algorithm which is worse than those algorithms, but this is just to illustrate the technique, and we will see that for other problems you get better algorithm using this technique. So, what is the natural thing? We've done this technique, this kind of thing several times. So, I have such a structure, a subset of size at most 2k that covers all the edges. This is an independent set. Now, I want to know whether there is a k size vertex cover. So, what is a natural thing to try? Yeah, we do not want to branch. Reduction or something like this. In fact, we did something like this in the first lecture when I said I have a graph which is k away from something, and we were trying to do something, right. So, for example, we said I have a graph which is k away from a tree or k away from a bipartite graph, and I want to find minimum vertex cover kind of questions we did, right. So, what did we do if you remember? Since this is of size at most 2k, I can guess the intersection of my solution with this, right. So, let us try that. So, I am going to try all. So, I am looking for a vertex cover size at most k, let us call it S prime. Now, S prime may intersect S in some number of vertices, it may not intersect at all, in that case the number of vertices it intersects is 0, but there are up to k possible intersection it can have, there is a vertex cover of size k. So, let me guess that and then see what is my new problem, and we will see that new problem becomes completely trivial. Okay. So, guess, so S prime is a solution of at most k we seek. So, guess S prime intersection S, right. It's this is at most k, right, because I am looking for a k size vertex cover. Okay. So, let me just guess. So, here is my S, let us say this is S prime. So, this is the, I like to call it in the solution, or let us say in my solution, and this is out of the solution I am looking for. So, this is S prime intersection S. Okay. How many choices do I have for these guesses? 2k choose k, right. There are 2k elements here. So, that is all nice f of k, right. In fact, it is some good f of k, 2 power k really. So, I have 2k choose k choices. So, now what is my remaining problem I have, right. So, this is v minus s, this is independent. So, now what am I looking for, right. Let us say this is some L which is less than or equal to k, 2k choose k choices for S prime intersection S. So, now what is the new problem? So, I say I am going to assume that this is part of my solution. It is a vertex cover problem. Once I pick it, I can remove this vertex. It is done. It's these set of vertices, right. So, now what am I looking for? What is the new problem? I have still a budget of how much? K minus L. Where do I choose from? Those set of vertices. From here, because I already made my guess here. So, I am not going to choose any more elements from here. So, now I have to cover all edges. This is independent anyway, there may be edges here. So, I have a new problem which is O here, this is V minus S. Find, or question is, does there exist a vertex cover S double prime of this G minus N? N is a subset of vertices I picked. G minus N is this remaining graph. With what properties? Cardinality of S prime is at most K minus L, because I am allowed K and I already picked some L vertices. What else do I, what other property I want? Yeah, I already said vertex cover. So it has to cover all edges. What else? That it should not intersect here, right? So S double prime intersection O is empty. Okay, so this is my new problem. I have made my guess here, so I delete it. For each such choice, right? For each such choice, I have a new problem. What is the new problem? I have this graph. There may be edges here. This is independent, and I want to cover all edges of this new graph by picking only vertices from here, and I am allowed K minus L. Okay. Can we do that? First of all, if O is not independent, you can't do it. It's a wrong guess. Move on to the next guess, right? So how do I solve this problem? Solution to this problem. If G, the induced subgraph on out, is not independent, because who's going to cover edges here? Only vertices here, but I've said I don't want any intersection. I made my guess of what I'm going to pick from S. So if G out is not independent, then no. This guess is wrong, I move on to the next guess. Okay. Otherwise, so suppose Y is independent. So what you have is actually a you have a bipartite graph where I am looking for a vertex cover of size K minus L. So you can apply bipartite graphs, polynomial time algorithm, find the minimum vertex, but it's even simpler than that, because it's not just, I can't apply a standard bipartite graph because I need to satisfy this condition. So, but I am saying this condition actually makes life even simpler, right? The edges are all only here, and I am not allowed to pick this is independent. I am not allowed to pick vertices here. So what do I do? What is the solution? Pick all vertices with the edges incident on them. In particular, pick all the neighbors of these vertices. All the neighbors of these vertices, they all have edges incident on them, and those edges need to be covered. The other endpoint is here, so I can cover it only by picking these vertices. Anything for which there is no edge incident on it, no problem, you don't have to pick. So else, but I want to check whether that budget is, if neighborhood of out is less than or equal to K minus L, then yes, else no. Right. So for every vertex here, I just pick its other endpoint, its neighbors, right? Collect them all. I need to pick them. I'm forced, because who's going to cover those edges? If you don't want me to pick anything from here, I need to pick those endpoints. Collect them all. I don't need anything else because there are no edges here. Collect them, and if that number is more than K minus L, then I'll say no. If it is less than or equal to K minus L, I solve the solution. So this is a complete linear time algorithm for a particular guess, but I have to run through so many different choices, and so overall my running time is 2k choose k times some polynomial. Okay, so this is usually called the compression problem. Because I am given a larger sized solution and I want to compress it to a smaller size solution. And anything that goes through iterative compression has this standard template. First thing is you guess. Since this is some f of k, guessing it is some g of k. So, try all possible subsets of some whatever size you are after, guess that, and typically you can get rid of those vertices. I mean, not always, but for vertex cover, feedback vertex set, you remove those vertices, and then what you have is actually called disjoint vertex cover problem. What is this? You are actually given a vertex cover, right? This is a vertex cover, right? Because it's a subset of a vertex cover, so it's a vertex cover. You are given a vertex cover. I am looking for a vertex cover for the whole graph, which is disjoint from this vertex cover of a particular size. Okay. So this is usually the entire template for iterative compression algorithm, except the compression problem is not so easy. For vertex cover, this turned out to be a completely trivial solution. For some other problem, we will see that it's harder. Okay, and in fact, the quite non-trivial part of the whole thing is in the compression part. Okay, so okay, and the running time, the f of k is a function of how big the starting set I have, right? So I will show you later that actually you can have a much smaller sized starting set without appealing to an approximation algorithm, but for now let us go with this. I want to run through the whole thing for undirected feedback vertex set. Okay. So recall, what is the feedback vertex set problem? You want a subset of vertices that will cover all cycles. Okay, it's an undirected graph. The problem makes perfect sense in directed graphs also, but it's a lot more complicated problem. Okay, we'll get to that sometime. For now, we are working with undirected graph. We want a subset of vertices that cover all the cycles. Remember what kind of an FPT algorithm we had? 3k to the k. That was the best so far we have seen, based on the idea that, of course, you do this minimum degree 3 pre-processing. After that, we said the top 3k degree vertices, one of them must be in any solution. That gave us a handle to branch. 3k power k was the best we had, but using this route, we will actually come up with the 5 power k algorithm, and that even better is known, but we won't get to it now. Okay, so I'm going to follow through the entire template just to show you that it works very similarly. So the compression problem, S is the feedback vertex set. What is the size? Well, again, for feedback vertex set problem, there is a 2 approximation algorithm. Okay, not so easy and not as easy as vertex cover, but there is a 2 approximation algorithm for feedback vertex set. So you can run that. If it produces solution which is more than 2k, you return no. Otherwise, you have something of size at most 2k. And then the question we want to ask is, so what do we know? So you have a feedback vertex set of size at most 2k is given to you. What do I know about this induced subgraph here? It's acyclic, it's a forest, okay, because it's a feedback vertex set, it's a forest. Good. So now let's come here. What do? We will guess the solution which we are seeking. What is its intersection with S? Suppose it's L. I pick that solution, delete it from the graph. How many choices I have? 2k, choose k. Okay, for now, but we will do a tight analysis later. So this part remains as it is, right? Now, what is the new problem? It's disjoint FES problem. What is the question? So I have a set of vertices here which I decided I am not going to pick for my solution from S. and I have, so what do I know about this is a forest, right? The question is, does there exist a feedback vertex set of S prime G minus N of size at most K minus L that does not intersect O? Okay. Now the solution is not that easy, at least the first step is more or less similar. What is the first step? If, what do I want this to, because I am trying to cover the cycles in this graph using vertices from here, right. Earlier we were covering all edges, now I am trying to cover all cycles from vertices here. So what should this satisfy? It should be a forest. So if G out is not a forest, then no. Okay. Now let us see what is the new problem we have, and then it requires some little work to get there. It is not immediate, unlike vertex cover where we just picked all its neighbors. No, we can't do that. We are trying to cover all cycles passing through both these parts. So there are all kinds of cycles. There may be cycle which goes through here, comes back here, or there may be, even this is a forest, there may be a cycle which goes. So there are all kinds of cycles we need to cover. Okay, so where are we now? We have a forest here out which induces a forest. Okay, so let me just write down, look at some connected components of this. And this is also a forest. So each connected component is a tree. My goal is to cover all the cycles across. And what is my budget? I have picked some L vertices. So this, what is its size? Is at most 2k minus L, right? Initially it was 2k. I have picked L vertices and removed them. And my budget is k minus L. I want to pick k minus L vertices from here. I can't pick from here, I am from here to cover all cycles. Okay. Now we will hit whatever we know so far, right? We will do some pre-processing, we will do some branching. So what pre-processing will, we can remove degree 1 vertices. Or even if there are isolated vertices from the graph, anywhere they don't form a they don't contribute to any cycle cover. Degree 2 vertices, recall what we did when we were designing our 3k power k algorithm. We did this short circuiting. Okay. We have to be careful here. So what was the argument for that? We said, well, if you have a degree 2 vertex, I might as well remove y and replace it by x z, because if you have a feedback vertex set that actually picks y, then its role is actually to cover a cycle that goes through y, because y is of degree 2, and any cycle going through y will have x and z. So you might as well pick x and z, and I have maintained the cycle. This was the argument when we said you can do this short circuiting. You have to be careful here, because there are certain vertices you are not allowed to pick here. I have declared myself that I do not want a solution to intersect this. So I can't, for example, if I have a a degree 2 vertex which looks like this, I can't say, oh, instead of this we might as well pick this vertex and draw an edge, because I can't pick such vertices. Okay. So, I have to be careful, but modulo that particular case, other degree 2 vertices you can handle. Okay. So, what are all possible degree 2 vertices? So, I have out and I have V minus S. So, if I have a degree 2 vertex here, I can do this short circuiting, no problem. That, the same earlier argument works. If I have a degree 2 vertex like this, I can do that, no problem. If I have a degree 2 vertex which goes like this, right, which has one neighbor here, again I can remove this and directly add this, because I can pick this vertex into the solution instead of this, right. This is still in this allowed part. The only other case is that if I have a degree 2 vertex where both its neighbors are here, do not do any short circuiting, leave it as it is. Okay. So, I am going to say short circuit degree 2 vertices, it's short, except for a vertex in B minus S whose both neighbors are in out, because that argument that if not this you can pick either one does not hold. But other than that, we will do this degree 2 rules. Now, okay, let us capture the budget. Sorry, K minus L, right. I have already picked L vertices into my solution. So, now I am allowed K minus L vertices. Let us see any other pre-processing we can do. Suppose you have a cycle in this graph where there is only one vertex from here, everything else is the other side, then what can you do? You have to pick that to cover that cycle, because I have declared that I am not going to pick anything from here. So, it is forced, include that into the solution, decrease your budget, right. So, what is that scenario? That if you have a vertex which has at least two neighbors, both are in the same connected component out here, then you know that that would form a cycle with only that vertex entered. So, reduction rule 3 I would add, if there exists a V in V minus S that is adjacent to two vertices in a component of the induced subgraph on out, then include V in the solution, so I am going to say the new K is actually K minus L, and your new K would be whatever the K minus 1. Now, you are picked one more into your solution, look for a feedback vertex set of size K minus 1. Okay. So, keep applying these three rules: degree less than or equal to 1, include, just get rid of it from the graph. Degree 2, do this short circuiting, and if you have a vertex which has two adjacent neighbors, but both to the same connected component in this induced subgraph out there, up there, then you pick it into the solution, because it forms a cycle. This is the only vertex of that cycle, so you need to pick it to cover it. Okay. Good. So, at this point we are going to do some branching. Okay. So, as I said, compression step is not always as trivial as it was for vertex cover, but it's still we are almost done. So, we are working on this disjoint feedback vertex set problem, where you are given a feedback vertex set, right. So, because this is a forest and I am looking for a feedback vertex set of the whole graph, which is disjoint from this with some specific budget. Okay, so now what I will do is following step 4. Pick any vertex V in V minus S that has at least 2 neighbors in the set out and branch. Okay, so what am I doing? So, after doing all this pre-processing, I pick some vertex here in this V minus S, which has 2 neighbors. Now, if it has at least 2 neighbors, we know that it is actually the 2 neighbors are in different components, because if it's the same component, we have pre-processed. So, I pick such a vertex, and what if there is no such vertex? We will come to that. If there is such a vertex, I am going to take it and branch on that vertex. What does branch on that vertex mean? In one branch, I will include it in the solution. In the other branch, I will exclude it in the solution. That's all. That's what in general branch on a vertex means, this, that I will include it in the solution. So, in one branch, V is in S prime. So, K goes to K minus 1. The other branch V is not in S prime. Okay. Now, you should complain. What is the complaint? K doesn't drop here. What do I mean? I made a big deal last time, said whenever you want to talk about branching algorithm, if not K, some function of K should drop. Okay. And we saw some SAT algorithm, we said, so you do some pre-processing so that K drops, but whereas here K doesn't drop. Okay. So, it is a very clever algorithm. It also points out some subtleties in branching algorithm. K doesn't drop, but I want to argue that there is some progress happens. What is the progress that happens? So, in this case I include V into the solution, in the other case I exclude V into the solution. It is same as saying I am going to throw V into my out set. Remember, that is the set from which I am not going to pick anything, right. So, what I will do is I will take V and add it to the out set and continue. Okay, still K doesn't drop. You did some magic about putting it in the outset, but so what? I say, okay, K doesn't drop, but something else drops. What drops? Yes, what drops? The number of connected components in out drops. Okay, what happens? Because since this guy, the vertex whose degree is greater than or equal to 2, necessarily has neighbors in at least 2 different components, because if it is same component I would have processed it. So, when I go and include it here, there is an edge like this, there is an edge like this. So, this 2 components merge. So, the number of connected components in out comes down. Okay. So, now I something comes down, right. K does not come down, something else comes down. So, let me change my measure now of my depth of this search tree, right. So, what I am going to do is to use a new measure. Okay, let us call some mu, which is a new measure for branching, as K, my solution size, right. This is the budget for solution size, plus number of connected components in the induced subgraph on out vertices. Suppose I write that as my measure mu. Okay. So, one important thing whenever I change the measure is to make sure that mu does not change, does not increase at least when I do these pre-processing rules. Okay, that is true because I by doing any of this I am not going to increase the number of connected components, degree 1, degree 2 connected components if any can come down, because I may have a degree 1 component that gets removed. So, number of connected components if any comes down or remains the same, it never increases. It is very important to check that. So, now when I do the branching, what happens? K drops, what happens to mu, right. So, when I include V into my solution, I delete V, right. Suppose in one branch I take V and include it into the solution. So, I delete V, K drops, K becomes K minus 1. Number of connected components here, nothing changes, they remain. I am not disturbed anything about this. So, they remain. So, mu decreases by mu minus 1 because K drops by 1. In this branch, I did not include K into my solution. So, K does not change, but the number of connected components decreases. So, mu becomes again mu minus 1. Okay. So, if I use my measure as a mu, then the height of this tree is 2 power mu. So, that is still a lot of little issues to deal with. How bad can mu be? First of all, right, is mu a function of K to start with, because otherwise all this is useless. What is the maximum value of mu? 3K minus L, right, because mu is for each choice, right, we fixed a choice. Yeah. So, mu is, now I will do some fine tuning. So, let us say actually 2K choose L, right, okay, we'll because I am picking L vertices and then I will sum over all possible L. Okay. So, mu is, first of all, my budget is K minus 1 L. So, I am looking for a solution of size K minus L. So, solution size is K minus L plus the number of connected components here, even assuming each connected component is a single vertex, the number of vertices here is at most 2K minus 1. So, that is, so it is at most 3K minus 2L. So, that is my at most 3K minus 2L. So, my depth 2 power mu is 2 power 3K minus 2L, that is 1. What happens when mu is 0? Okay, solution size is 0, so I can check whether the whole graph is acyclic in polynomial time, no problem, right. So, I mean I want to be able to check in polynomial time at the leaves. What happens at the leaves? At the leaves mu is 0. Mu cannot be 0 because number of connected components will not be 0. So, mu will be, at least when K is 0, you can check that in polynomial time. So, at least when, as long as the number of mu is at most the number of connected components, then you can check in polynomial time. So, at the leaves it is not a problem, because you just have to check whether the given graph is acyclic. Is there a solution of size 0? You can do that in polynomial time. So, now let us take stock of my, so this is it, right. One more thing to be worried about. What if there is no such a vertex? Will it? Let us see why.
Because then you will be able to apply rule 2.
No, see, no, what is the thing here? I have a vertex which is 2 neighbors, both of them are here. It may have a large degree, but that is inside B minus S. So, that
Not rule 3.
Well, Rule 3 only if we have two neighbors are out there. I am just saying, suppose there is no vertex here which is both neighbors out there. Is that possible? Remember, it's a forest. You said there is no cycle. Yeah, each you have a collection of trees below and a collection of trees above. And what does it mean by in this? This is the, and here I have trees, and I am saying that I have no vertex here which has both neighbors out there. Is that possible? Right? When is it possible? Take any leaf vertex in one of the trees. Okay, take any leaf vertex in one of the trees. Clearly, that is not degree 1 in the whole graph because of rule 1, right. So, its degree is at least 2, and it has one neighbor here, and if the other neighbor is here, the other neighbor has to be there because it is a leaf vertex. But then it makes it only degree 2, and such a degree 2 vertex we would have pre-processed it, right. So, that vertex definitely should have at least 2 neighbors out there. So, any leaf vertex in any of the trees qualifies here. Since bottom you have only a collection of trees, pick any leaf vertex in one of the trees. It may even be a single vertex by itself. It's okay. How do I let it be there, right? How do these rules allowed it there? Because it has 2 neighbors out there, and I am not allowed to touch it. That's only two, at least 2, maybe even more. If you have more than 2 neighbors, that's good news, right? Why? Suppose I have a vertex which has at least 3 neighbors. What do I get? Okay, what happens in this branching? Yes, right, because this vertex cannot have 2 neighbors into the same component, all 3 must be to different components. So, the number of components comes down because this vertex, when I add it, it merges these 3 components into one, so it drops by 2, so it's even better. Okay, so we will use that idea and improve the running time later. Why should such a vertex exist, and if not, we can deal with it separately. But for now, here is my entire algorithm. Okay, first of all, so we will do this degree 1, degree 2 rules and this rule, then you are guaranteed to have a vertex of this type. Any leaf in any of the trees in the bottom graph will be one such vertex. Take that vertex and branch. In the branch, you include it in the solution, don't include it. Don't include it means you decrease the number of connected components. So, let us now carefully see what is the overall running time, right. So, overall running time, there is this. Summation L equal to 0 to k, right. That is the number of different choices for my guess at the bottom, at the top. 2k choose L into, I have a 2 power mu. For each such choice, I have this branching step and some polynomials I am ignoring, right. And what is mu? What is the upper bound for mu we saw? 3k okay. So, this is some sort of a mess, but we will do a cleaner analysis. But even see L can go up to k only. So, even if I upper bound this by 2k choose k, which is roughly 2 power k. So, then you will have 2 power 4k. Okay. So, let me write, this is a very crude upper bound, we will make it, bring it down to 5 power k very soon. So, summation L equal to 0 to k 2 power k, I am just upper bounding 2k choose k. So, that is 4k minus 2L. Okay. And even ignoring this 2L, this is like k times 2 power of 4k. Okay. At least it is a c power k. Okay. The best we had was like 3k power k, it gives you c power k, but it is, let us see where are all the places where we have chance to improve. Okay. It turns out instead of starting with this 2k approximation algorithm, you can start with something much smaller, and that gives you a lot of room to get this bound to much cleaner bound. So, let us get to that. That takes us to this notion of iterative part. Okay. So, there are two places for room for improvement. One is that in this branching, as I said, if you manage to find a vertex whose degree is at least 3, it has at least 3 neighbors out there, it gives you a better running time. Okay. But if such a vertex does not exist, we need to deal with it. I cannot always guarantee such a vertex. Okay. But this kind of a vertex I can guarantee, some leaf in some tree will satisfy that. Okay. That is one problem to deal with, to get something improved f of k. The other thing is, which is pretty easy, is that instead of starting with 2k, we can start with something simpler. Okay. So, suppose I start with a k plus 1 sized solution, right, the smallest f of k larger than k. So, let us do it both for vertex cover and feedback vertex set and see what happens. Suppose a k plus 1 sized vertex cover. Okay. So, now problem, the compression step is I give you a k plus 1 sized vertex cover and ask you, can you tell me is there a k sized vertex cover, and we will run through the same algorithm, nothing different. We will make our guess for vertex cover. Once we make a guess, the problem was immediate, right. We say that this is what I am going to pick, this is something I am not going to pick. Once I decide that I am not going to pick these vertices, I am forced to pick their neighbors, and that is it, end of the algorithm, right. So, that is a polynomial theorem algorithm. Then what is the running time here? Then is summation k plus 1 choose I going from 0 to k, right. You see this? Because what was the algorithm, if you recall, we had a k plus 1 sized vertex cover. So, this was independent. Then I say, okay, I make a guess here of some I elements I included into my solution. These are vertices I do not include in my solution, which means I am forced to, I mean, if this is not even independent, I move on to the next guess. If this is independent, then I just go and pick all its neighbors here into the solution. That is some polynomial time computation, right. So, the only exponential thing is it's k plus 1 choose I, right, try all various I choices and then run over I has choices from 0 to k. And what is this? If I go up to k plus 1, what is this? Yeah, right. So, this is at most 2 to the k plus 1. Okay, so it is not really 2k choose k something heavy, it is simply a nice simple 2 power k plus 1 algorithm if somebody gave me a magic k plus 1 sized vertex cover. Okay, I need to worry about that. Who gives you and why do I get? At least 2k was obvious by an approximation algorithm, but who gives me a k plus 1 size solution? Well, we'll come to that. Again, there is a very simple, nice trick to get that. Let's try that for feedback vertex set, right? Feedback vertex set. After I make the choice, it's not polynomial time. You have a branching step, so there is some exponential time. You need to put that in. Let's do the calculations, right? If we start with a k plus 1 sized FES, right? So, what's the algorithm again? So, here is a k plus 1 size FES. I make some guess of size L, I remove it. Now, in the remaining thing, I do some pre-processing and then I branch, right? And then I pick a vertex and either I include it in the solution or put it in up there. So, what is the running time? Summation k plus 1 choose L, L going from 0 to k, that is the size of the intersection. After that, some polynomial pre-processing steps which I will ignore. So, 2 power what? Then we had a two-way branch, right? 2 power mu. What is mu here now? Let us be careful here. Mu is, what is my new budget? K minus L, right? I picked L and I am allowed K. So, K minus L plus how many components are here? Maximum k plus 1 minus L, right? Because this is what I am left with. This I delete. This is k plus 1 minus L. So, it is at most 2 into k minus L plus 1, right. So, 2 power this number, this is mu. So, 2 power mu, which is at most let me take the 2 out. So, the plus 1 I am going to take it out, it is 2 power mu. So, mu has this plus 1. So, that 2 I am going to take it out and this is what I put in. Actually, I can put, no, let me actually put here to make life easier. This makes it, I have made an extra 2 square. So, it is half. Okay. So, it is 2 power 2 into k minus L plus 1, but I am going to write this. So, this is equal to 2 into k plus 1 minus L minus 1, right. So, 2 into k plus 1 L minus L I have put, then minus 1 comes here. Okay. So, now what is inside the summation? So, this is 2 power 2. So, let me write this as 4 power. So, k plus 1 choose L times 4 power k plus 1 minus L. So, what is this? Hmm? 5 to the k plus 1, right. Even if I go all the way up to k plus 1, binomial theorem, x plus y whole power n is n choose I into x power I y power n minus I. So, that is what it is, right. So, basically this is 1 plus 4 power k plus 1. K plus 1 choose L into 1 power L into 4 power k plus 1 minus n. So, I have a 5 power k plus 1 by 2 algorithm, nice and cute, there is nothing, no machinery, nothing, it just runs through iterative compression template, right. We assume there is a k plus 1, of course, I need to deal with this, I haven't come to that, that's the last 5-minute suspense, right. So, I assume if I have a k plus 1 size solution, then I just make our guess, delete those vertices, do some pre-processing on the remaining, pick a vertex which has at least 2 neighbors out there and branch. In one branch, the solution size drops, in the other branch, the number of connected components on the upper set drops. So, if I use the measure as the size of the solution plus, so this is a very useful thing for branching. Okay, sometimes k may not drop, but some other progress happens and you may be able to capture it by a different measure. So, overall they have a very cute nice 5 power k plus 1 algorithm. Okay, we struggle for log n power k, 3k power k and all that, it is 5 power k plus 1. Okay, so now how do I get rid of this assumption that somebody has given me a k plus 1 sized solution? Okay. So, this is the iterate step. Right. So far we have been talking about compression step, where somebody has given me a larger size solution, we are able to compress it in some FPT time, right. How do we? Okay, so I have this graph where I am looking for a vertex cover or feedback vertex set. Let us say feedback vertex set, right, vertex cover is almost immediate. Okay, so let us say the vertex set is 1, 2, 3 up to n, and I take the first I vertices and call it Vi, and Gi is the induced subgraph on the first I vertices. Continue Panava. They can see this. Okay, so let's I want a k plus 1 size solution for the whole graph G, right. So now can you give me a k plus 1 size solution for G k plus 1 or k plus 2? Is that obvious? So, I do not want it for the whole graph. I take the first k plus 2 vertices of the graph, look at the induced subgraph. In that, can you give me a k plus 1 sized solution, right? Feedback vertex set. Yes, pick any k plus 1 vertices, that is a solution, right? because the remaining vertex is alone and there is no cycle in the remaining graph. Good. So, I now take that g k plus 2, which is a graph on 1, 2 up to k plus 2 vertices. There I have a k plus 1 size solution, give it to my compression algorithm and ask for this graph, not for the whole graph, but for g k plus 2, can you compress it and give me a k size solution, right. If it comes back and says no, I cannot, there is no k size solution for this, what does that mean? There is no k size solution of the whole graph, right, because I am not able to cover cycles even here using k vertices. How do you expect me to cover for the whole graph? Okay. Now, this is an important property you need. Okay. This may not be true for several other problems. For example, for dominating set, something like dominating set, I may not be able to find the k size dominating set here, but if you include some more vertices, I may be able to find. Okay. So, this is very important critical property you need to apply this iterate step. Okay. So, I take this graph, give it to my compression step and say, can you give me a k plus 1 size solution, k size solution, and if it says no, I will say no, the whole graph does not. If it says yes and gives me a k size solution here, I take one more vertex, expand my graph, add that one more vertex into my solution also. Now, I have a new graph with one extra vertex for which there is a k plus 1 size solution. Give it to my compression algorithm. Can you compress it to a k size solution? If it says no, I will say no. If it says yes, I got a k size solution. Take that k size solution, add extra one vertex, keep doing. Right. Finally, I will have the whole graph for which I will have a k plus 1 size solution, you can compress it. Now, what happens to the running time? That is it. Whatever the running time, I mean 5 to the k time something was already there. Okay, I ignored the polynomial time, but whatever that running time was, there is a multiplicative factor of n, actually n minus k, that is it. Okay, very cute, right? Just absolutely simple, there is nothing magic going on. And so, the important thing is that you need to be able to conclude that if the solution, if there is, it is a no for a subgraph, it is a no for the whole graph, right. At least it is true for vertex cover, at least it is true for feedback vertex. Okay. So, k plus 1 size solution for g k plus 2, yes, take any k plus 1 vertices. Now, apply compression step on g k plus 2. If compression returns no, return no, else include one extra vertex, right? I mean include v k plus 3 into the solution, or vertex k plus 3 into the solution to get a k plus 1 size solution for g k plus 3 continue here. Right, we have a k plus 1 size solution, apply compression. If compression returns no, you can get out of the entire algorithm. If it gives you a k size solution, take that solution, add k plus 3 into the solution. So, whatever, so the next iteration it will be something else. You have a k plus 1 size solution, apply compression. So, overall runtime n minus k times, because I start with k plus 2, time for compression. So that gives you, O star 5 power k for FES and 2 power k for vertex cover. And this 5 has been improved to 3.618, basically using this branching, that if there is a vertex which has 3 neighbors, you can do it, and otherwise there is a polynomial way to handle it using some matroid theory there. Some machinery is required at this bailing out of the recursion. But 3.618 has been the best for a long time. So improving this is an interesting open problem. So now let me just throw a couple of problems which we will continue tomorrow. But what I want you to do is to just run through the template and get up to the compression step, and then think about the compression step, and we'll work on it tomorrow, right? So the two problems. So yeah, this has been feedback vertex set. As I said, people tried branching, kernelization, and one could not get C power k. And to get a C power k, you needed this interesting iterative compression technique. So now we don't need to go to approximation to get us the starting set, right? We can just do this iterative procedure. All we needed, this important property that if this subgraph has no solution, then our graph has no solution. Okay. So two other important problems we will deal with, and again they had some very elegant solution using this. Is this odd cycle transversal? So what is the problem? You want to cover all odd cycles. Okay, you want a subset of k vertices whose removal makes the graph bipartite. There are no odd cycles, right? So does there exist S contained in B kernel to S less than or equal to K, G of B minus S is right. So you can start with the K plus 1 size solution, iterate, get onto the compression step, do your guess, right? You're given a K plus 1 size solution, you guess it, and then you are left with this disjoint version of the problem. At least proceed up to that point, okay? And then, for every problem you need a different algorithm for dealing with the compression step. But up to that point, it's a standard template, okay? So it's a good practice. Just try that, and then we'll get to the compression step. And here, this was the first problem for which this compression, iterative compression technique was used. They did not call it iterative compression. It was some algorithm published in some operations research letters, and parameterized complexity community picked it up, found good application of this for a lot of problems. Feedback vertex set. So for this is a problem we have not seen it at all, right? I don't think we have seen. Have we? No. Right. Oh, good. Okay. Somebody is following. Yes, we did reduce this problem to vertex cover above matching, right? We took this 2 copies of the graph, made matching, and then using that we had a 4 power k algorithm, right? Vertex cover above LP, and that gave us a 4 power k algorithm. Using iterative compression, we will improve it to 3 power k. Okay. Another problem is feedback vertex set. In directed graphs, that was another problem problem for which iterative compression was used. It was a long open problem. Finally, an FPT. We won't get to it tomorrow because that requires another technique, separators, and so on. But feedback vertex set in tournaments has a very nice algorithm using iterative compression. What is that? Does there exist S contained in V such that is acyclic, and what is G? G is a tournament. What is a tournament? It's an orientation of a complete graph. So, between any pair of vertices, there is exactly one directed edge. Is there an easy FPT algorithm for this? Okay, so we are trying to kill all directed cycles in a tournament. I'm not sure we discussed this. We did. It was an assignment question. Okay. So whoever did not copy this should be able to tell. There are hints there anyway. Right? So what is the easy FPT algorithm? So here's a very nice simple observation. See, whenever you want to cover a cycle, and if I want to use a branching algorithm, what do? I find a short cycle, and I can say that at least one of the vertices in the cycle must be in my solution and gives me a branching, right. The problem here is with the size length of the cycle. If the cycle is too large, then the branching factor increases. But in a tournament, one can show a tournament is acyclic if and only if it has no triangles. It means you just check whether it's acyclic. If so, you're already done. If not, you can find a triangle in the tournament. So it gives you a three-way branching, 3 power k. Right? Using iterative compression, we'll improve it to 2 power k. So why is this true? So if you have a large cycle, since it's a tournament, there is a directed edge between every pair of vertices. Look at the chord, either it's going in this direction or that direction. Either way, you will get a shorter cycle. Right? So if it's not a triangle, so you will always, if there is a cycle, it will have a triangle. So you can find a triangle, branch. Once you have a triangle, you know one of the endpoints must be there in any solution. Gives you a three-way branch, right? So just try iterative compression, go as far as you can, at least up to the compression step, and we will look at the compression step of both these problems tomorrow. Okay, so we will improve this to and for this we saw using vertex cover above matching, we will improve to so one other observation useful to keep in mind is that typically if the compression step is some 4 power k kind of an algorithm, sorry, this is not the compression, this is the disjoint version step, right. Compression step is the overall thing. The disjoint version, where you have you already made your guess and you have a solution, you want something disjoint from that. If that takes some c power k, then the overall thing would be like c plus 1 power k. Like here 4 power something gave rise to, because if you include the guesses you are making, overall if you do the calculation, it will be c will become c plus 1. Okay. So, the 3 plus 1 should tell you, 3 power k should tell you what sort of running time you are looking at for the disjoint version. Similarly, the 2 power k means that we are actually solving the compression step in polynomial time, right? That is like vertex curve. Okay. Okay. So, we will see tomorrow.